Postulates of quantum mechanics. These postulates help us to understand the quantum mechanics. Okay, what are the postulates? I can summarize initially. First postulate is about the representation of a state in quantum mechanics. So usually represent by some notation. So we can take psi. So we can represent a state of a quantum mechanical particle by a state psi. And this state is psi is specified in a space, that is Hilbert space and all. Okay. And another thing is how to get information from psi. So if we know the wave function psi, then we can extract all the information about the particle, like its momentum, its energy, its position, etc. And third postulate is regarding the time evolution. This also we already discussed, that if we have a wave function at a time equal to 0, we can find out that wave function at a time t. So the postulate tells us how to represent a state, how to get information from that state, and how to find out the time evolution of that state. So let us discuss in detail. So the postulate 1. Postulate 1 is about state of a system. That is how we can represent the state of a system and all. That is, in classical mechanics, we have a coordinate system. That is our Cartesian coordinate system or 3D space. Any coordinate system, polar coordinates, spherical polar coordinates, or anything. Okay, so this is a 3D space. Okay, 3D coordinate system. Let us consider this as a Cartesian coordinates x, y, z. So in this coordinate system, that is in this space, we can specify the particle momentum, position, and all. Okay, similarly, so this means position, momentum, and energy means the state of the particle. Similarly, in quantum mechanics, we use a space, that is Hilbert space. This is quantum mechanical space. And this space is spanned by some basis vectors. Here we see x, y, z. These are the basic vectors, basis vectors, that is x cap, y cap, z cap. They are orthogonal to each other. So similarly, in Hilbert space also we have basis vectors. So suppose this Hilbert space is spanned by 3 basis vectors, that is psi 1, psi 2, and psi 3. Suppose this is the basis, right? Psi 1, psi 2, psi 3. Similarly, in classical mechanics or in 3D space, the basis is x, y, z. So any quantity can be represented or described by using this basis. Similarly, in quantum mechanics, we can use this basis to represent any state. So a state can be spanned by a combination of these basis states, that is Ci, Psi I. It is similar to a vector, that is r vector in a Cartesian coordinate system, that is x I cap plus y j cap plus z k cap. Similarly, we can represent the state of a particle by using linear combination of this basis. That is, this is a linear combination. So the state of the system can be represented by linear combination of this basis in Hilbert space. That is, psi is equal to, if here there are 3 basis, so psi will be equal to C1, psi 1 plus C2, psi 2 plus C3, psi 3, where C1, C2, C3 are the constants. And this wave function can represent the state of the particle only if mod c1 square plus mod c2 square plus mod c3 square is equal to 1. Because these are the probability of finding the particle in various states. Okay. Therefore, the total probability of finding the particle should be equal to 1. That is mod c1 square plus mod c2 square plus mod c3 square should be equal to 1. That is, this condition is called normalization. So, the normalized wave function only can represent the physical particle. Now, how we can represent the state? That is representation of psi. So, the state can be represented in two ways. One is we can represent the state in a position space, or we can represent the state in a momentum space. That is, position space is the vectors, that is, bases are position, that is, this is spanned by, the space is spanned by r vectors, and the momentum space is spanned by momentum vectors. There is equation we can transform one position space to momentum space or vice versa. That we will discuss later. And one more thing, there is completeness relation. That is, space is complete or not. That is what the completeness relation tells us. That is summation over r ket r vector bra r vector. If it is giving equal to 1, then the space is complete. That is, position space is complete. And if for momentum space, summation over p ket p vector bra p vector is equal to 1, then the momentum space is complete. And this one is called as outer product. Or it is called as projection operator. Now the postulate 2. What is postulate 2? Postulate 2 is about operator. That is, every physical quantity is represented by an operator. That is, position operator x cap, momentum operator p cap, right? And this operator has certain properties. That is, operator which is mathematically linear and Hermitian also. We discussed these ideas earlier, right? A linear operator and a Hermitian operator. There is various examples also we discussed. One is energy operator, that is I h cross dou by dou t, and momentum operator, that is minus I h cross dou by dou x. Okay, all are mathematically linear operator and all are Hermitian operator also. Postulate number 3. Postulate 3 is about measurement. That is, I told you, operator is a device which acts on the state and will give the measured value, right? That is, suppose A is an operator, it is acting on some state psi, then it will give the measured value and that state itself. So this is a eigenvalue function. In Dirac notation, we can represent this as operator A get psi is equal to lambda get psi, right? And now I am going to multiply this throughout by bra psi. So what we will get? We will get bra psi operator A get psi is equal to bra psi lambda get psi. Here lambda is a constant value, so we can take it outside. That is bra psi operator get psi is equal to lambda bra psi get psi. What is this one? This is nothing but equal to 1, right? Because inner product with the same state will be equal to 1 because they are normalized. So we got lambda, that is eigenvalue is equal to bra psi operator psi. This is nothing but, that is lambda is equal to expectation value of A. That is eigenvalue is nothing but expectation value. Okay. Here we are discussing about measurement. So there is a chance of uncertainty in measurement. That is, what is this uncertainty in measurement? That is delta. Suppose A is the operator, then uncertainty in its measurement will be delta A. Okay, so I am going to define this operator, that is operator A acting on certain state psi, then it will give a eigenvalue and that state itself. That is, this one is a eigenvalue equation. Okay, after the measurement, the state of the system is not changed. Okay, that is psi here, same size here. Okay, so this is an eigenvalue equation. Now, I want to find out uncertainty delta A. What is this equation? We already discussed this one. That is, this is equal to expectation value of A square minus expectation value of A square. So we have to find out expectation value of A. What is expectation value of A? That is psi A psi. So here we know this is in a Dirac notation. We can write this as this one. Okay. So when A operator act on this state vector get psi, we will get a lambda psi. That is bra psi. When this operating, then we get lambda get psi. That is, we got expectation value of A is equal to lambda, because this is equal to, we can take this lambda outside into bra psi get psi. This one is equal to 1. So we got this equal to 1. That is, we got expectation value of A is equal to lambda. So we got this value. Now we have to find out what is expectation value of A square. That is A square acting on state psi. That is, this operator is like A operating on A. Okay. This is the expansion of A square operator. So first this A operator will act and then this operator will act. So when A act on that one, we get, see, A operating on psi. So we'll get lambda get psi. Now again, that is lambda we can take outside. So operator into get psi. Now again this will operate on this one. That is lambda into lambda get psi. Okay, that is we got lambda square get psi. So again I want to find out the expectation value of A square, that is equal to bra psi A square get psi. That is equal to, so I have to multiply the left hand side of this equation by bra psi, that is bra psi lambda square get psi. Here I can take this lambda square outside, that is lambda square into bra psi gets psi. You know, this is normalized, so it is equal to 1. That is, we got expectation value of a square is equal to lambda square. Now we can put these two equations, two values in this equation. So we get delta A, that is uncertainty in the measurement of operator A is equal to root of what is A square expectation value, that is lambda square, minus what is expectation value of A, that is lambda. So we have to take square of it, that is again lambda square, that is equal to 0. That means if it is an eigenvalue equation, that is when operator operate on a state and it will give the measured value and the same state, okay, then the uncertainty in the measurement is 0. Now I am going to discuss some eigenvalue equations, examples for eigenvalue equations in quantum mechanics. First example is energy, that is, you know, H psi is equal to E psi. Okay, Hamilton operator operates on the state and it will give the energy and the same state. And second one, L square operator, that is angular momentum operator operating on a state, then it will give L into L plus 1 h square into that same state. And the third example is LZ, Z component of angular momentum. If it operates on some state, it will give ML h cross and that state itself. So these are examples for eigenvalue equation. But all are not eigenvalue equations. If not eigenvalue equation, then okay, so we are going to discuss one condition, that is we are going to discuss about not an eigenvalue equation. That is, if an operator operates on certain state psi 1, so it will give some measured value, that is lambda, and give another state. So after measurement, the state of the system is changed to psi 2 from psi 1. So this is not a eigenvalue equation. And if it is not an eigenvalue equation, then there will be uncertainty in the measurement. That is, delta A is greater than 0. That is, there is uncertainty in measurement. But here, if it is an eigenvalue equation, then uncertainty is equal to 0. I tell you a classical analogy for not an eigenvalue equation. So here I told you this one is an operator, that is a measuring device. So I am taking a measuring device, that is pressure gauge. Okay, so this pressure gauge is the measuring device, that is operator, right? So this pressure gauge is operating on air in the tire. So we are going to measure the air pressure in a tire of some vehicle. Okay, how this pressure gauge will work? If we connect this pressure gauge to tire, some air in the tire will enter into the pressure gauge and meter will shows that pressure. Okay, so some air in the tire is leaked to pressure gauge. So we get a measured value, that is we get pressure inside the tire and we get air in the tire. But I told you some air in the tire goes into the pressure gauge. So now the air in the tire is decreased. So this is initial and after measurement it is changed. So this is final. So definitely the air pressure in tire after measurement will be slightly decreased. So if you are doing this measurement again and again and again, the pressure in the tire will decreases. Okay, that means here an operator is operating on a state So we got the measured value and that state is changed to another state. So if you are measuring again on the same system, see its state is changed. So we never get the same eigenvalue again. So after every measurement, eigenvalue also will change. Like this case. So in first measurement, we will get a pressure value P1 and we get a state psi1. If you again try to measure the pressure, that is now the air in tire is P1. Okay, so when we are measuring that pressure we get a pressure P2 and the air pressure will be decreased to another pressure level, that is side 2. Okay, this is a classical analogy for understanding this eigenvalue, not eigenvalue equation. But eigenvalue equation means after measurement, the state of the system never changes. That is, measuring some property of the system never change the system. That is eigenvalue equation. Postulate number 4. Fourth postulate is about probability. That is, let us consider a particle in a box case. So there is a system. In that system, the particle can exist in any of the 3 states. So this is psi1, psi2, psi3. So this particle can be found at any of the state, and there is a probability of finding the particle in psi1 state, that is P1, psi2 state, that is P2, and psi3 state, that is P3. That is, the basis is psi1, psi2, psi3. And the state of the system is a linear combination of psi1, psi2 and psi3. That is summation I, Ci, psi I. So we can expand, that is equal to A1, psi1 plus A2, psi2 plus A3, psi3. And I told you P1, P2, P3. P1 is the probability of finding the particle in the state psi1, and P2 is the probability of finding the particle in state psi2, and P3 is the probability of finding the particle in state psi3. Now I want to find out these probabilities P1, P2 and P3. How we can find out P1? That is, P1 is equal to bra psi1 get psi mod square by bra psi get psi mod square. So what we will get? We will get this is equal to modulus of A1 square by modulus of A1 square plus modulus of A2 square plus modulus of A3 square. And if we evaluate for P2, we will get modulus of psi2 get psi mod square by modulus of bra psi get psi mod square. That is equal to modulus of A2 square by modulus of A1 square plus modulus of A2 square plus modulus of A3 square. Similarly, if you evaluate for P3, that is probability of finding the particle in the state 3, that is bra psi 3 get psi mod square by bra psi get psi mod square, that is equal to mod A3 square by mod A1 square plus mod A2 square plus mod A3 square. So from these equations, we can find out a simple formula for finding the probability. That is, probability P is equal to modulus of amplitude square by summation of modulus of amplitude square. For an example, our state is psi is equal to A1 psi 1 plus A2 psi 2 plus A3 psi 3. I want to find out the probability of finding the particle in the first state, that is P1. Then this will be equal to amplitude of the particle in that state, that is A1, that is modulus of A1 square by, see, these are the amplitude of various states. So take sum of amplitude squares, that is modulus of A1 square plus modulus of A2 square plus modulus of A3 square. So we got the same answer. Okay, so this is the equation for finding the probability of particle in certain state. If a linear combination of state is given and they are asked to find out the probability of finding a particle in particular state in that linear combination. Okay, let us discuss one more example. A state is given, that is linear combination of two states, that is given as root 2 by 3 psi 1 plus I root 1 by 3 psi 2. The question is to find out probability of finding particle in the state psi 1 and probability of finding the particle in the state psi 2. So the probability of finding the particle in the state psi 1 is represented as P1, that is equal to, what is the equation? Modulus of amplitude square. So the amplitude of the state is root 2 by 3, that is root 2 by 3 mod square divided by summation of amplitude squares. So that is root 2 by 3 mod square plus, here this state has a certain amplitude, that is modulus of I root 1 by 3 mod square. So this is equal to 2 by 3 divided by 2 by 3 plus 1 by 3, that is equal to 2 by 3 divided by 3 by 3, that is 1, that is equal to 2 by 3. Now we can evaluate the probability of finding the particle in the second state, that is psi 2, that is P2. That is we have to find out this, amplitude, that is this one is the amplitude, that is modulus of I root 1 by 3 square by summation of amplitudes, that is mod root 2 by 3 mod square plus mod I root 1 by 3 whole square. That is we get, see again denominator is equal to 1. So this is equal to 1 by 3. See, you can see, here you can see, if you are adding this probability P1 and P2, you can get 2 by 3 plus 1 by 3, that is equal to 1. That is total probability of finding the particle in that system is equal to 1. Average of an operator. Suppose we have some states, that is state is a linear combination of different states, that is psi 1, psi 2, psi 3. That is the state of the system is linear combination of psi 1, psi 2 and the psi 3. Okay, now an operator acts on it, operate on it. So what we will get? If this is an eigenvalue operator, it will give eigenvalue, right? That is the eigenvalue corresponds to psi 1 is lambda 1 and psi 2 is lambda 2 and psi 3 is lambda 3. So this is the measured value, some measured value of psi 1. And here the state of the particle is a linear combination of different states. So there is a probability of finding the particle in the state psi 1, that is denoted by P1, and probability of finding the particle in the state psi 2, that is P2, and it is P3. So the probability that is P1, P2 and the P3. Probability of finding the particle in state psi 1 is P1, psi 2 is P2 and psi 3 is P3. Now we have to find out the expectation value. That is nothing but average value. We already discussed, that is expectation value of operator. Then what will be the expectation value or average value of this operator? That will be equal to lambda 1 P1 plus lambda 2 P2 plus lambda 3 P3. That is We can write it as a summation over states lambda s ps. That is expectation value or average value of an operator is equal to summation over states lambda s ps. Lambda s is the eigenvalue. So I tell you one example. There are different states. States are same psi1, psi2 and psi3. Actually this is a actually this system is in a state psi. So these are the different components of that state. That is the state psi is a linear combination of psi1, psi2 and psi3. And now we are going to operate energy operator, that is Hamiltonian operator. So what we will get? We will get the eigenvalue, that is a Hamiltonian operator, that is energy operator operate on a state, it will give the energy of that state. So from psi1 state we will get energy E1, psi2 state we will get energy E2 and E3. And finding the particle in each of the state is different. So the probability is P1, P2 and P3. Then the average energy or average value of Hamiltonian operator will be equal to E1 P1 plus E2 P2 plus E3 P3. That is average value of energy of a system is equal to summation S, that is summation over states ES PS. Okay, this is a special case of this general expression. Example problem. A state is given. The state psi is equal to 1 by root 3 psi1 plus root 2 by 3 psi2 plus I by root 3 psi3. And if Hamiltonian operates on psi1, that is energy operator operates on psi1, it will give the energy of the state psi1, that is given E psi1 and H acts on psi2, it will give 2E psi2 and H acts on psi3, it will give 3E psi3. Now the question is to find out average value of E. That is nothing but expectation value of E. That is the question. So how we can solve this? We know expectation value of energy is equal to summation over states ES PS. That is ES is the energy of each state. That is for state psi1 energy is E. For state psi2 energy is 2E. For state psi3 energy is 3E. Okay, so that is ES, energy of each state, and PS is the probability of each state. Because this is a linear combination of states, so particle may be in any of these states, psi1 or psi2 or psi3. But there is a probability of finding the particle in each of the state, that is P1, P2 and P3. So here we know ES values, right? Now we have to evaluate this PS values, that is P1. I told you how we can find out the probability from a linear combination of states. That is, we have to find out probability of finding the particle in the state psi1. So we have to take the amplitude, that is modulus of 1 by root 3 mod square by amplitude square of all these states. Okay, that is modulus of 1 by root 3 square plus modulus of root 2 by 3 square plus modulus square of I by root 3. So what we will get? We will get 1 by 3 by 1 by 3 plus 2 by 3 plus 1 by 3. That is equal to 1 by 3 divided by 4 by 3. So we get this is equal to 1 by 3 into 3 by 4, that is 1 by 4. Okay, similarly we have to find out for P2, that is P2 is equal to modulus of root 2 by 3 whole square by this value. This entire value is equal to 4 by 3, that is by 4 by 3, that is equal to 2 by 3 by 4 by 3, that is 1 by 2. And we can find out P3 also, that is P3 is equal to modulus of I by root 3 whole square by 4 by 3, that is 1 by 3 into 3 by 4, that is 1 by 4. Here also you can add all the probabilities, that is, see, if you add P1 plus P2 plus P3, then you will get this is equal to 1. That is, the probability of finding the particle in that system is equal to 1, but probability of finding the particle in each of the state is different, that is P1, P2 and P3. Okay. So now we can substitute all these values in this equation. So average energy will be is equal to summation S ESPS, that is E1 P1 plus E2 P2 plus E3 P3. So what is the E1 energy? That is E into P1. What is the probability? That is 1 by 4 plus what is E2 energy? That is 2E. It is already given, right? Into P2. P2 is 1 by 2 plus what is E3? E3 is 3E into what is P3? That is 1 by 4. So adding these terms, we will get this is equal to 2E. Another example, wave function psi is equal to 1 by 2 psi 1 plus I by root 2 psi 2 plus 1 by 2 psi 3. So this is the state of a dynamical system, and H psi n, if Hamiltonian operator operates on a state psi, then it will give n square E psi n. That means if H operates on psi 1, it will give n values 1, that is 1 square E psi 1. Okay, that is E psi 1. Similarly, if H operates on psi 2, it will give 2 square, that is 4 E psi 1. And if it's operated on psi 3, it will give 3 square, that is 9 E psi 1. So these are the energy values E1, E2 and E3. Okay, so the question is to find out average value of energy. So we know average value of energy is equal to summation over S ES PS. Okay, that is, here we got E values, that is E1 is this one, E2 is this, E3 is this. Now we have to evaluate PS. Okay, so first we have to evaluate P1, that is equal to modulus of the amplitude of psi 1, that is 1 by 2 square by 1 by 2 square plus I by root 2 square plus 1 by 2 square, that is equal to 1 by 4 by, if you are squaring, we will get 1 by 4 plus 1 by 2 plus 1 by 4, that is equal to, this one is equal to 1, that is 1 by 4. That is, this is a normalized wave function. That is why this value is equal to 1. If it is not normalized, we will get some other value. Now we have to find out P2. That is, P2 is equal to mod I by root 2 square by denominator. Denominator value we know, that is equal to 1. Okay, so this is equal to 1 by 2. And P3. P3 is equal to 1 by 2 mod square, that is 1 by 2. Now we have to find out average value of E, that is summation over S ESPS, that is E1 P1 plus E2 P2 plus E3 P3. So we know what is the value of E1. E1 is E into probability of first state, that is P1, that is 1 by 4 plus E2 is 4E into P2 is 1 by 2 plus E3 is 9E into P3 is 1 by 2. So by adding these terms, you will get the answer, average energy. Okay. Another example, if E1 is equal to 10 EV and E2 is equal to 30 EV, then find average energy of the following. So first one is psi is equal to 1 by root 2 psi 1 minus 1 by root 2 psi 2. So here what is the question? We have to find out expectation value of E, that is equal to summation over S ES PS. So here only two states and this is equal to E1 P1 plus E2 P2, where E1 is given, E1 is 10 EV and E2 is also given, that is 30 EV. We have to find out only P1 and P2 and substitute those values here. So what is P1 here? P1 will be equal to this is 1 by root 2 square by 1 by root 2 mod square plus 1 by root 2 square. That is, we get 1 by 2 divided by 1 by 2 plus 1 by 2, that is equal to 1 by 2. Here also this value is equal to 1, means the wave function is normalized one. Okay, so we got P1. So if P is, see here actually you don't want to evaluate P2 in the same fashion because there is only two states. Okay, earlier I told you if you sum over the probability you will get 1. Okay, so there are only two states. So for one of the state it is 1 by 2 and there is only one other state. So other state will have a probability 1 by 2, then only the P1 plus P2, that is summation over P1 is P1 plus P2, not P1, summation over P, okay, will be equal to 1. So P2 is definitely equal to 1 by 2. Okay, so now we can substitute all those values here, that is expectation value of E is equal to E1 P1, that is 10 into P1 1 by 2 plus E2 is 30 into P2 is 1 by 2. So find out the answer. We got the average value of energy. Now second question. So earlier we given the condition for E1 and E2. So it is a continuation of that same question. That is, second one is psi is equal to root 2 by 3 psi 1 plus I by root 3 psi 2. Find average E. Third question is psi is given, that is equal to root 3 by 5 psi 1 plus root 2 by 5 psi 2. Again find average value of E. And fourth one, psi is equal to 1 by 2 psi 1 plus root 3 by 4 psi 2. Find average E. So here the E1 is equal to 10 EV and E2 is equal to 30 EV. Okay, so please solve it. This is a work for you. Average energy of linear harmonic oscillator and a hydrogen atom. First we discuss about linear harmonic oscillator. It is 1D linear harmonic oscillator. One-dimensional linear harmonic oscillator. So for one-dimensional linear harmonic oscillator, the energy expression En is equal to n plus half h cross omega. That is, for a linear harmonic oscillator, it can have different states, psi 1, psi 2, psi 3, psi 0 also. Okay, that is a ground state. So, for that is, these are the psi n values. For this one, ground state, n value is equal to 0, first excited state, n value is equal to 1, and so. Okay. So here, for the ground state, there is an energy, that is, for ground state n is equal to 0. So the energy is equal to E0 is equal to, we have to substitute n equal to 0 here. So we will get half h cross omega. And the energy of first excited state is equal to, we have to substitute n here. So it is 3 by 2 h cross omega, and E2 is equal to, we have to substitute 2 here, right? So it is 5 by 2 h cross omega, and so on. Okay, so these are the states and corresponding energies of a linear harmonic oscillator, 1D linear harmonic oscillator. Now we can discuss one question. That is, question is, a state is given, that is psi is equal to root 2 by 5, psi 0 plus 1 by root 5 psi 1 plus root 2 by 5 psi 2. So the particle is in a state which is a linear combination of various states of a linear harmonic oscillator. So the question is to find out average energy. We know the equation for average energy, that is, average energy is equal to summation over states ES PS. So here first we have to see, here ES we already obtained, right? That is, E0 is equal to half h cross omega, E1 is equal to 3 by 2 h cross omega, and E2 is equal to 5 by 2 h cross omega. Now we have to evaluate PS, and we know how to evaluate PS value. That is, first we have to evaluate P0, that is, probability of finding the particle in the state psi 0. So that is root 2 by 5 mod square by mod square of root 2 by 5 all square plus mod square of 1 by root 5 plus mod square of root 2 by 5. So this is equal to 2 by 5 divided by 2 by 5 plus 1 by 5 plus 2 by 5. That is, this is equal to 1, right? That is, this wave function is also a normalized wave function. A normalized wave function only can represent the particle, the real particle. Okay, if it is not representing, and if this value is not equal to 1, then we will do the normalization. Then only that wave function can represent the particle. Okay. So here it is normalized wave function, that is why it is equal to 1. So this is equal to 2 by 5. That is, we got P0 equal to 2 by 5. Similarly, we will get P1 equal to 1 by 5, and we get P2 equal to 2 by 5. Now we have to substitute these values in this expression for average energy. So that is, average energy E is equal to E0 P0 plus E1 P1 plus E2 P2. That is, we know E0 is equal to half h cross omega into P0 is equal to 2 by 5 plus E1 is 3 by 2 h cross omega into P1 is 1 by 5 plus E2 is 5 by 2 h cross omega into P2 is 2 by 5. So by multiplying all these terms, you will get 3 by 2 h cross omega. Here the only difficulty is you should know about the equation of energy for 1D linear harmonic oscillator. Hydrogen atom. For hydrogen atom, the wave functions are represented by psi n l m, where n l m are quantum numbers, or sometimes it is represented as ket n l m. Okay, and I think you know the energy expression for hydrogen atom, that is En is equal to minus 13.6 eV by n square. So here I am representing this as E by n square, where E is minus 13.6 eV. Okay, this is just for simplifying the calculation, that is in the final expression we will substitute for E. Okay, so the question is, a wave function is given, that is psi is equal to 1 by root 2 psi 1 0 0 plus 1 by 2 psi 2 1 0 plus 1 by 2 psi 2 1 1. The question is to find out the average energy. How we can find out? We know the expression for average energy is equal to summation S ES PS. So we have to evaluate the ES values and the PS values. Okay, so first we can evaluate ES values. That is, what is E1? That is, here these are the n values. Okay, so only the n value depend the energy. All other parameter n or m doesn't depend on the energy. Only n parameter. So here it is n value is 2 and here it is 2. Okay, so for these two states the energy will be same. Even it is psi 210, here it is psi 211. But n value is same for both of these states. So the energy of these two states will be equal. So what is E1? E1 is the energy of this one, right? So n value is equal to 1, that is E by 1 square, that is E. Now E2. E2 is this state, right? That is E2 value is equal to, when n equal to 2, it will be E by 4. Now we have to evaluate PS. For the state psi 100, the probability is modulus of 1 by root 2 square divided by modulus of 1 by root 2 square plus 1 by 2 square plus 1 by 2 square. That is, you will get 1 by 2 divided by 1 by 2 plus 1 by 4 plus 1 by 4. That is, this is equal to 1. That is 1 by 2. Similarly, for state psi 210, you will get 1 by 4, and for state psi 211, you will get 1 by 4. Okay, so we got the probability, and this one is for the state psi 100. This is for the state psi 210, and for psi 211 also the energy is equal to, that is n value is 2, so this will be E by 4. Okay, so now we can find out the average value E, that is first one, that is the state. So the energy is E into probability is 1 by 2 plus second state, the energy is E by 4 into its probability is 1 by 4 plus third state, the energy is E by 4 into its probability is 1 by 4. Okay, so multiplying this you will get answer. That is the average energy of a hydrogen atom. That is hydrogen atom in this particular state. You just multiply and find the final answer. So finally you will get an equation in the terms of E. So you have to substitute for this E, that is minus 13.6 eV. Okay, so you will get the average energy of this state. Okay, here also the only difficulty is you should be familiar with the energy expression of hydrogen atom. So please remember this expression.